Alright, on this lovely snowy day, I thought I would make a video covering some of the beginning material in Chapter 10, which is our next chapter. There's not going to be another lecture in class because we want to keep moving and not get too far behind, just because of a snow day. So I will expect that you're familiar with the material in this lecture on Wednesday and on Friday, because that's when we'll look at some example problems. And so if you're not familiar with it, you won't really know how to go about doing those problems. So Chapter 10 is about the moment of inertia. And we should be familiar with the moment of inertia from general physics, although we're going to quickly transition into a more engineering approach or more engineering definition of moment of inertia. But first of all, we want to remind ourselves from general physics, what does the moment of inertia quantify about an object and how do you calculate it? So in general physics, we learn that the moment of inertia is a body's resistance to a change in its rotational state. So it's very similar to inertia. Remember that the inertia of an object is its resistance to a change in its linear motion. That comes from Newton's first law. An object in motion will tend to stay in motion unless acted on by an outside force, and an object at rest will tend to stay at rest unless acted upon by an outside force. And so we quantify that object's inertia by its mass. So just sort of making a quick transition into rotational motion, the moment of inertia of an object talks about how an object that is rotating will tend to keep rotating, or an object that is not rotating will need some sort of torque to make it start rotation. And so a measurement of its resistance to change in that rotational state is the moment of inertia. So how do we calculate it? The calculation of the moment of inertia, if you remember, is related to the distribution of mass relative to a given axis of rotation. So if we have a finite system of masses that are located at specific locations in the xy plane, for instance, the moment of inertia is just the sum of those individual masses times their distance to the axis squared. This actually ends up being a shorthand notation or words that we sometimes use for the calculation of moment of inertia, where we said it's the sum of the mr squares. So notice that it is related to the mass, just like inertia is, but it's also important, where is that mass in relation to the axis of rotation? The r squared ends up sort of making it so if you have mass distributed symmetrically about an axis, masses don't end up canceling out with positive and negative values when you're calculating the moment of inertia. If you have a mass distribution, as you might expect, the calculation of the moment of inertia changes from a summation into an integral. And so it's the integral of r squared times dm. All right, so that's how we define the moment of inertia in general physics. When we go into the engineering realm, the moment of inertia most often is going to be viewed from the point of view of the area instead of looking at the mass. So let's look at an example. So here we have a plate that's submerged in a liquid, and the pressure of the liquid at a given distance y is given by gamma y. Remember, gamma is the value of the gravity times the density. And so they call it the specific weight of the liquid. Okay, so remember, this is sort of similar to the things that we looked at in the end of chapter 9 when we talked about pressure. Notice that this pressure can almost act like a distributed load, where the strength of the load gets stronger as we go deeper because of the fact that it's proportional to y. And so when we look at this, so if we look at a particular area at a certain depth, a depth of y, the force exerted on that area is the pressure times the area element, dA. So here's the force, pressure times dA. And then the moment about the x-axis is going to be y, the distance from the x-axis, times that force. And then the total moment is of the area, we would integrate that value. And so the moment is going to be y dF, which is going to be y times the pressure times dA, which is going to be y. Now remember, the pressure was gamma y dA. And so this ends up being gamma y squared dA, and that's how we calculate the moment. So let's start that. So the moment, again, here's what I just did. The superscripts aren't coming out. And what we talk about is we refer to this integral as the moment of inertia of the area of the plate about an axis. So it sort of comes out in this situation that this calculation, it gives us something very similar to the moment of inertia, but we're talking about the area distribution. The reason that we care about the moment of inertia of an area is it actually helps an engineer figure out the strength and deflection of a beam when they're doing the calculations to see, how sturdy something's going to be. So what we want to do now is we want to talk a little bit about the calculation of the moment of inertia of an area. So this is going to be very similar to how in the chapter 9 we started off talking about the center of mass and the center of gravity, which was how mass and weight was distributed relative to a certain coordinate system. Now, and then we went into the centroid, which was more the distribution of the area. That we're going to do the same thing here with moment of inertia, is we're going to talk about more how the area is distributed relative to a particular axis. So here, let's say we have just an arbitrary area, dA, or A, the total area is A, and so different definitions of the area moments of inertia. For instance, relative to the x-axis, of course, we're talking about dA. The distance of that area from the x-axis is measured in y, so that would be defined as y squared dA. Similarly, we would have for the y-axis, the distance of that dA is given by the x-coordinate, so that's x squared dA. And then we also have another distance here, notice in this picture, is this distance r, and we're going to call that the polar moment of inertia, where it's r squared dA. Notice that this is actually the moment of inertia around the z-axis. And so if we look at the moment of inertia, some of these things aren't coming through right. It's y squared dA. Here, let's just get rid of these because these aren't working. So I sub x is y squared dA. Iy is equal to x squared dA. And we had written j sub naught as r squared dA, but keep in mind that r squared is x squared plus y squared, And so it turns out that we could find the moment of inertia about the z-axis could be given by Iy plus Ix. Another quantity that we run into in engineering is this term, the radius of gyration. And basically the idea is, you have a given moment of inertia. And let's just call it I. What distance from the axis would you place the entire area so that you would have the same moment of inertia? And so this distance that you're trying to find, is called the radius of gyration. So that's the definition of what the radius of gyration is. The way that we calculate is we would say, for instance, the moment of inertia about the x-axis would be equal to kx squared times a, and so this is the radius of gyration. So kx would be the square root of that moment of inertia over the a. And similarly, for the y moment of inertia, so it basically kind of gives you the idea of how far away the area would be from the axes. And this actually is of use to engineers when they're designing columns, and so that's why we actually would care at all about this. Now, it turns out that a theorem that's going to be useful for you to use is called the parallel axis theorem. And the parallel axis theorem has to do with calculating the moment of inertia of a certain area if you know the moment of inertia when the axes go through the centroid. But the idea is that now you're not trying to find the moment of inertia around those centroid axes, but around axes that are parallel to them. And that's why it's called the parallel axis theorem. After we see this, we're going to see that we use this a lot in calculating the total moment of inertia of composite masses. So that's something that is going to be similar to what we did in Chapter 9, where we found the centroid of a composite mass using the centroids of the individual pieces. Here we're going to do something similar, but first of all, we need to know this parallel axis theorem. You might remember using this in general physics. For instance, we knew the moment of inertia about the center of a rod when the axis went through the center. Well, then we could use the parallel axis theorem to calculate the moment of inertia when the axis went around one end of the rod instead. So here you see in this picture, this is the centroid right here. And so these are the centroid axes, the y primes and the x prime. And then what we're trying to find is these are the axes that we want to calculate the moment of inertia about. Notice that all that we've done is we've moved these new axes. They've moved some distance away from the axes that go through the centroid, and they've only moved parallel. Notice there's no sort of rotational motion or anything, and that's kind of important because we can't do that. So what we're going to do is we're going to see how we do this calculation. All right, so we're going to start off with, let's just, for example, do the moment of inertia about the x-axis, and that's this axis right here. And so here we have the area, and then this distance here we would call y, measured in that coordinate system. So the moment of inertia would be y squared dA. But notice that that y is actually the addition of dy plus y prime. Now the y prime is the coordinate of dA in the prime system, and dy is the distance of between these two axes. That's the distance that the axis has been moved, and this is all squared. Now if we expand that square, we get dy squared plus 2 dy y prime plus y prime squared dA. And so we can sort of divide this up into 3 separate integrals. And also recognize some of the terms are constants, so we can just take them outside of the integral. All right, so let's just go on to the next page. What we had for Ix was that it was equal to dy squared dA plus 2 dy y prime dA plus y prime squared dA. And so that's where we are so far. And what we're going to do is we're going to look at this middle term. And the basic integral that we're dealing with here is y prime dA. But remember, the definition of the centroid of y prime is y prime dA over dA. But in our primed coordinate system, the centroid, C, is at the origin. So y prime centroid is 0, which means that this integral of y prime dA is also 0. So when we look at our expression for Ix, this whole middle term vanishes. And what we get here, Ix is dy squared times a, and then this is just the moment of inertia about the x-axis for when the axis goes through the centroid. And so that is our result. We have Iy will be similar. And so would J0. So this should look sort of familiar in terms of how we looked at or learned about the parallel axis theorem in general physics. Remember, it was a d squared times the mass. Now we're dealing with the area, so it's a d squared times the area. And the moments of inertia for different axes going through centroids is another thing that you can find in the inside cover of your textbook. So if you might remember that you might have even noticed those terms when we were looking at centroids, because the pictures have common geometric shapes like semicircles, rectangles, etc. And it gave you the x and y coordinates of the centroid, but you might not have noticed, or you may have noticed, they also gave you the moments of inertia through the centroid, when the axis was through the centroid. And so those are values that you can look up. You can look these up in the book. And so that's really going to be handy for us when we talk about composite areas. And that's the last thing that we're going to talk about today, is finding the moment of inertia for a composite area. And basically, the composite area is just like we did in the previous chapter. So you have some shape, but you can break it down into simple shapes like triangles, rectangles, and circles. And so here we have a shape that is a triangle. It's also then two rectangles. And one of the rectangles, of course, is going to be treated like a hole. And so we'll subtract that. And so basically, what I had already said is that you could find the moment of inertia about the axes going through the centroid in the inside back cover of your textbook. And what we can do is, if we want to find the moment of inertia of this entire object, we can use those values along with the parallel axis theorem to help us find the total moment of inertia of this object. And so basically what we would do is we take the shape and divide it into its parts. Like this example, we have a rectangle and a circle, and we want to find the centroid of each piece, and then we have to find the distance of that piece to the axes. And so look, it's just a reminder, I have to go to mechanics, but we're not going to go. And so we're going to use that in calculation. Then what we do, again, subscripts aren't working here, is the moment of inertia about that x-axis is going to be the moment of inertia of each shape about the centroid axis plus the total area times the distance that we've moved the axis. Distance is in the y direction, right? That's what we move. And so those are how we find the moment of inertia of each piece. Then what we do is we simply add all the individual pieces together to find the total moment of inertia, keeping in mind that if we have a hole, that we just simply subtract it. And so this is really going to be all that I want to talk about. As you might realize, I haven't done any example problems, but I wanted to save that for class. And like I said before, I do expect you to be familiar with this material that we did in this sort of video lecture. Tomorrow, you'll be responsible for having your homework done, and we'll go over homework problems, and then we'll do some example problems from this material. Hope you have a good day.